For 20 years, the story was simple. Quantum computers would kill the GPU. Machines like the ones NVIDIA builds would become relics, museum pieces, next to whatever came next. That story just died. Because NVIDIA didn't wait to be replaced. It reached out, grabbed the thing that was supposed to replace it, and wired it directly into its own machines. Let that sink in for a second, because it is a genuinely strange, almost contradictory move if you only know the popular version of this story. The version most people have absorbed from headlines and science fiction alike. For years, the headlines have told us that quantum computing is the next great leap, the technology that will make today's supercomputers look like abacuses, pharmaceutical breakthroughs computed in seconds instead of decades, materials designed atom by atom, encryption broken and rebuilt from scratch. The message, over and over, was that classical computing, the kind of computing GPUs do, was a stepping stone, a placeholder, something we would eventually outgrow. So when the company that makes the most powerful classical computing chips on the planet announces that it is now physically wiring those chips into quantum processors, you have to ask what it knows that the rest of us don't. And the answer, once you understand it, completely flips the script on how we should think about the future of computing. To understand why NVIDIA would make a move like this, you first have to unlearn a little bit of what popular science has taught you about quantum computers. Most explanations focus on the exotic parts. The idea that a qubit can be a 0 and a 1 at the same time, or that two particles can be entangled across space in a way that seems to defy ordinary logic. Those explanations are not wrong, but they leave out the part of the story that actually determines whether any of this becomes useful in the real world. And that missing part is control. A quantum processor, no matter how many qubits it has, is completely useless without an enormous, precisely timed support system watching over it every microsecond of its operation. That support system has always been the hard part. It has always been the part that nobody puts on a conference slide, because it is not as glamorous as talking about parallel universes. It is just engineering. But it is engineering that determines everything. Here is the secret nobody puts in the headlines. Quantum computers are extraordinarily fragile. A qubit, the basic unit of quantum information, is not like a bit in your laptop, sitting there stubbornly holding its 0 or its 1 no matter what happens around it. A qubit is more like a soap bubble balanced on the tip of a pin in a hurricane. The tiniest vibration, a stray photon, a fluctuation in temperature, even cosmic rays passing through the lab, can knock it out of its delicate quantum state. This is called decoherence, and it is the single biggest obstacle standing between quantum computing as a laboratory curiosity and quantum computing as a tool that actually solves real problems. To keep a quantum processor useful, you cannot just build the qubits and walk away. You need constant supervision. You need systems watching the qubits thousands, sometimes millions of times per second, recalibrating them, correcting the errors that creep in, and doing it fast enough that the correction happens before the quantum information collapses into uselessness. Think of it like trying to keep a spinning plate balanced on a stick while someone keeps bumping the table. You cannot fix that problem once and forget about it. You need a constant high-speed feedback loop that reacts faster than the plate can fall. And that feedback loop requires an enormous amount of classical computation, not quantum computation. Classical, the kind GPUs are extremely good at. This is the part of the quantum story that rarely makes it into the popular narrative, because it is less exciting than talking about parallel universes and superposition. But it is the part that actually determines whether quantum computing has a future outside of academic papers. NVIDIA's own leadership has been blunt about this. Their argument is that the quantum processor is like a brilliant but chaotic artist, producing something extraordinary but completely unable to organize itself, while the GPU plays the role of the disciplined studio manager, constantly providing the tools, catching the mistakes, and keeping the whole operation from falling apart. Jensen Huang, NVIDIA's chief executive, put it even more directly when he explained why his company felt it was essential to connect a quantum computer straight to a GPU supercomputer. He said it was necessary so that error correction could happen, so that artificial intelligence could calibrate and control the quantum computer in real time, and so that classical and quantum systems could run simulations together as one unified machine. That is the reasoning behind what NVIDIA built, and what it built is called NVQLink. NVQLink is not a single chip or a single product you can hold in your hand. It is an open architecture, a kind of universal adapter designed to let quantum processors and NVIDIA's accelerated computing hardware talk to each other with almost no delay. It was first unveiled in October of 2025, and the ambition behind it was not to replace quantum computers, and not to make GPUs obsolete either, but to fuse the two together into something new. A hybrid system where the quantum processor handles the parts of a problem that only quantum mechanics can handle, and the GPU handles everything else, the calibration, the correction, the orchestration, All of it happening in a loop so fast that the fragile quantum state never has time to fall apart. The numbers behind this are almost hard to believe if you are used to thinking about computers in terms of processing power rather than pure speed. NVQLink is described by NVIDIA as the most powerful classical resource ever connected to quantum processors, achieving latency as low as 4 microseconds, 4 millionths of a second. To put that in perspective, a single blink of your eye takes somewhere around 100,000 microseconds. NVQLink can shuttle information between a GPU and a quantum chip, have that GPU perform a correction calculation, and send the result back, all within a sliver of time 25,000 times shorter than the blink of an eye. That is the speed required to keep a quantum system from collapsing into noise. What makes this even more significant is that NVQLink was not built to work with just one type of quantum computer. There are actually several competing physical approaches to building a qubit right now. Some companies use superconducting circuits cooled to temperatures colder than deep space. Others trap individual ions in electromagnetic fields. Some use photons of light. Others use neutral atoms held in place by lasers. For years, this fragmentation has been one of the underappreciated problems in the quantum industry, because a control system built for one type of qubit often does not work for another. NVQLink was designed to be agnostic to all of it. It works across superconducting qubits, trapped ion systems, photonic systems, and neutral atom systems alike, giving every major approach to quantum computing access to the same high-speed classical backbone, and giving every quantum hardware company a reason to plug into the same NVIDIA ecosystem, rather than build their own competing infrastructure from scratch. At the center of the software side of this is something called Q2Q, NVIDIA's platform for writing code that runs across CPUs, GPUs, and quantum processors as if they were all part of one machine. This is arguably just as important as the hardware interconnect itself, because without a common programming model, even a perfectly fast physical connection would be useless. Researchers need a way to actually write and run hybrid algorithms without having to become experts in the specific wiring of whatever quantum machine happens to be sitting in the next room. Q2Q is NVIDIA's attempt to be that common language, and NVQLink is the pipe that carries the data back and forth in real time. Think of it this way. Imagine you had built the fastest highway system in the world, capable of moving cargo between 2 cities in a fraction of a second. That highway would still be worthless if every truck that used it needed a completely different custom-built engine depending on which factory it came from. Q2Q is the standardized engine. NVQLink is the highway. Together, they mean a researcher working with a superconducting quantum processor in one country and a researcher working with a photonic quantum processor in another can, in principle, write strikingly similar code, deploy it on strikingly similar hardware, and expect it to behave the same way, even though the underlying quantum physics inside their machines could not be more different from one another. That kind of standardization has been one of the quietly persistent obstacles slowing the entire quantum industry down, because so much engineering time has historically been spent reinventing control software from scratch for every single new piece of hardware. When NVIDIA first announced this in October of 2025, it was not just a philosophical pitch. It came bundled with concrete infrastructure. NVIDIA revealed 2 new supercomputers being deployed at Argonne National Laboratory, one named Solstice and one named Equinox, containing 100,000 and 10,000 of NVIDIA's Blackwell generation GPUs, respectively, expected to become operational in the first half of 2026. These are not modest machines. They represent some of the largest concentrations of computing power ever assembled, and the fact that they are being built with quantum integration in mind from day one tells you how seriously NVIDIA is taking this bet. And it was not a bet NVIDIA was making alone. From the very beginning, the announcement came with an unusually large coalition behind it. 17 different quantum hardware builders and 9 United States national laboratories signed on to help shape NVQLink, including Brookhaven National Laboratory, Fermilab, Lawrence Berkeley National Laboratory, Los Alamos National Laboratory, MIT Lincoln Laboratory, Oak Ridge National Laboratory, Pacific Northwest National Laboratory, and Sandia National Laboratories. These are not marketing partners looking for a press release. These are the institutions responsible for some of the most serious scientific computing on the planet, and their involvement signals that NVQLink was being treated less like a product launch and more like the foundation of a new kind of scientific infrastructure. The proof that this was more than theory came just 1 month later, in November of 2025, when a company called Quantinuum used NVQLink together with Q2Q to pull off something remarkable.